Welcome to the Curious Voyager. It's lovely to have you here wherever you are tonight. Maybe you're tucked under a blanket with the lamp still glowing in the corner. Maybe you're on a train watching the dark slide past the window. Maybe you're simply lying still in the quiet, letting the day finally let go of you. Wherever you are, settle in. There's nothing you need to do for the next little while except breathe and drift and let me carry the thinking for you. And before we begin, just so I know who I'm speaking to in the dark, where in the world are you watching from tonight? I always love imagining it. Some of you are deep into the small hours, the streets outside gone silent. Some of you are watching as the light fades, the evening only just settling in. If you'd like more nights like this one, more slow, strange, beautiful journeys to fall asleep to, a gentle like and subscribe really does help this sleepy little channel keep going. Small creators like me rely on your kindness more than you'd think. And to those of you already here, already part of this, thank you. Truly. You're the reason there's a next one. Now, I'll make you the same promise I always make. I'll try not to make this so interesting that it keeps you awake. But if it does, well, at least you'll have learned something. A fair trade, I think. And honestly, you don't need to follow every word. You don't need to understand all of it, or any of it really, not tonight. If you drift off somewhere in the middle, that's perfectly fine. The ideas will still be here when you wake. We'll move slowly, softly, one small mystery at a time, with nowhere to be and no rush at all. So let me tell you about something that right now sounds almost impossible. And I want you to just picture it as we go, gently, the way you'd watch clouds move. Somewhere on Earth, in a quiet room, behind a closed door, inside a machine no bigger than a kitchen table, there is a place colder than anywhere in the entire known universe. Not a place in some distant galaxy. Not the dark between the stars. A place here, on our own planet, made by human hands. A spot so cold that the numbers almost stop meaning anything. A billionth of a degree above the lowest temperature that can possibly exist. And then later, colder still. A trillionth. A coldness so deep and so complete that something happens to matter that has no name in everyday life, because it never, ever happens in everyday life. Here is what happens. Imagine a tiny cloud of atoms, thousands of them, each one a separate, restless little thing, jittering and bouncing, each one its own private speck, like a crowd of strangers in a station, all moving, all going their own way, none of them quite touching. That's what atoms are normally, a crowd, a swarm, a multitude of separate selves. But cool them down, slowly, gently. Take away their warmth, which is really just their motion, until they grow stiller and stiller and stiller still. And at a certain point, a point unimaginably close to the absolute floor of cold, something tender and strange occurs. The atoms stop being separate. They forget, in a sense, that they were ever individuals. They merge. They flow together into a single, shared thing, thousands of atoms surrendering their separateness and becoming, all at once, one. Not one clump, not one solid lump, one wave. A single quantum wave, spread out smooth and silent, all those thousands of atoms now moving as a single ripple, a single breath of matter. Physicists sometimes call it a superatom because it behaves not like a crowd anymore, but like one enormous, gentle, unified thing. You could, in principle, photograph it. You could point a camera at thousands of atoms that have dissolved into a single quantum wave and capture the picture. And people have. This is the fifth state of matter. It's called a Bose-Einstein condensate. And tonight, Slowly, softly, we're going to drift all the way through the story of it. How a man dreamed it on paper in 1924. How it took 71 years before anyone could hold it in a lab. And how, by 2022, we had reached a cold so profound it's hard to even say the number out loud. There's no need to grasp every detail. Just let the wonder of it wash over you, the dissolving of many into one, the coming to rest, the great quieting. It's a fitting thing, really, to fall asleep to. Let me say that word again because it's a strange and lovely one and we'll be living with it all night. Condensate, a Bose-Einstein condensate. Bose, that's Satyendra Nath Bose, an Indian physicist. And we'll meet him properly a little later. Einstein, yes, that Einstein. The two of them, names joined across an ocean and across decades, attached forever to the coldest, stillest matter that has ever been made. We'll get to them. There's time. But first I want to set the scene properly, because to understand why this fifth state is so astonishing, you have to remember the other four, the four states of matter you already know in your bones, even if you've never thought of them in those words. So let's go slowly through them the way you'd run your fingers along familiar things in a dark room. There's solid. A solid is matter where the atoms are locked tightly together, holding hands, more or less, vibrating in place but never wandering off. A piece of ice, a stone, the wooden frame of your bed, the atoms are bound into a fixed shape, and that's why a solid keeps its form. It doesn't pour, it doesn't drift, it holds. Then there's liquid. Warm a solid up enough, give those atoms a little more energy, a little more freedom to move, and the bonds loosen. The atoms still cling to one another, but loosely now, sliding past each other like dancers who've let go of their grip. That's a liquid. Water in a glass, tea cooling beside you. It has no fixed shape of its own. It takes the shape of whatever holds it. Pour it, and it flows to fill the space. Warmer still, and you reach gas. Now the atoms break free entirely. They let go of each other completely and fly off in every direction, spreading out to fill any container they're given, bouncing, scattering, no longer clinging at all. The air around you right now is gas. Countless molecules zipping past, invisible, filling the whole room. Solid, liquid, gas. Cold, warmer, warmer still. You've known these three your whole life. And then there's the fourth, which you may know less well, but which is actually the most common state of matter in the entire universe. Plasma. If you heat a gas to a truly ferocious temperature, the kind of heat you'd find inside the sun, or in a bolt of lightning, or in the glow of a neon sign, the atoms get so violently energetic that they begin to tear apart. Their electrons get stripped away, and what's left is a churning, glowing soup of charged particles. That's plasma. Stars are plasma. The sun is a great ball of it. So in a way, most of the visible universe is in this fourth state, blazing away in the hearts of stars. So that's the ladder, the familiar ladder we climb by adding heat, solid, liquid, gas, plasma. Colder to hotter, more bound to more free, more ordered to more wild. Add energy, and matter loosens and breaks apart and flies wider. But here's the thing, here's where it gets quietly strange. What happens if you go the other way? What happens if, instead of adding heat, you take it away? And not just a little. Not just down to the cold of a winter night or the cold of a freezer, or even the cold of the polar ice. What if you took the heat away almost completely? What if you cooled matter down past every cold you've ever felt, down toward the very bottom, the absolute floor, the place where cold can go no further? Then you don't climb the familiar ladder at all. You step off the edge of it entirely into something new, into the fifth state, into a kind of matter that is the opposite of plasma in every way, where plasma is the hottest, wildest, most broken apart thing, atoms torn to shreds in the heart of a star. The Bose-Einstein condensate is the coldest, stillest, most unified thing. Atoms not torn apart but drawn together, not flung wide but gathered into one. It belongs to none of the other four states. It isn't solid, isn't liquid, isn't gas, isn't plasma. It's its own thing entirely, categorically different. The fifth state of matter. And I should be honest with you because honesty is part of the calm here. Scientists don't all count the states the same way. Some say there are more than 5. There are other strange, ultra-cold, quantum kinds of matter, things with names like superfluids and supersolids and fermionic condensates, that some physicists like to count separately. The bookkeeping gets a little blurry at the very bottom of cold. But the fifth state of matter, that's the name the condensate has carried into the world, the standard, beautiful shorthand for it, and it's a fair one, so that's what we'll call it tonight. The fifth state, the cold one, the one made of stillness. Now, I keep using this phrase at the bottom of cold, the floor, the place cold can go no further, and I want to slow down and tell you what that actually means, because it's one of the loveliest ideas in all of physics, and it's exactly the kind of thing to turn over gently in your mind as you drift. You see, heat is really just motion. That's the secret at the center of it. When something is hot, its atoms are moving fast, jittering, bouncing, vibrating, racing around. When something is cold, its atoms are moving slowly. That's all temperature really is, a measure of how much the atoms are moving. The warmth of your tea is the speed of its molecules. The chill of the night air is the slowness of its. So now ask the natural question, the simple question that turns out to be bottomless. If cold is just slowness, and if cooling something down is just slowing its atoms, then what happens if you slow them all the way down? What happens if you take away all the motion? If the atoms slowed and finally came to perfect rest, utterly still, not moving at all, that point, at the point where, in the simplest picture, all motion would cease, has a name. It's called absolute zero, and it sits at a very specific place, minus 273.15 degrees Celsius. That's how cold it is. Minus 273 degrees and then some. Far, far colder than the coldest winter that has ever swept across the earth. Colder than the poles. Colder than the highest, thinnest air. Because that's such an important number. Physicists gave it its own scale, say its own way of measuring temperature that starts right there at the very bottom. It's called the Kelvin scale. And on the Kelvin scale, absolute zero isn't minus 200 and something. It's simply zero, 0 Kelvin, the bottom of the ladder, the floor of cold. You start counting up from there. Room temperature, the comfortable warmth around you now, is about 300 Kelvin, 300 degrees up from the bottom. We live our whole lives, you and I, 300 steps above the floor of cold, and we call it warm, and we call it cool, and we never once feel how close to the top of the ladder we really are. So you might think, well then just cool something down to 0 Kelvin, take away all its motion, stop the atoms completely, reach the very bottom. And here is one of the deepest, gentlest truths in all of physics. You can't, not ever. No matter how clever you are, no matter how much money or genius you pour into it, you can get closer and closer and closer to absolute zero, a tiny fraction above it, a sliver, a whisper. But you can never quite arrive. Absolute zero can be approached endlessly forever, but never actually reached. This isn't just because the engineering is hard, though it is. It's a law. It's woven into the structure of the universe itself. It's called the third law of thermodynamics, and what it tells us, in plain words, is this. The bottom of cold is a place you can journey toward forever, and never set foot upon. Each step closer costs more than the last. The closer you get, the harder the next sliver becomes, and the very last step, the step that would take you all the way to perfect stillness, all the way to zero, that step can never be taken. The universe simply won't allow it. There is always the faintest trembling of motion left. I find that strangely comforting lying here in the dark. The idea that perfect stillness is something the universe holds just out of reach. That even the coldest, quietest matter ever made still carries within it the tiniest whisper of motion. Never quite fully at rest. Never quite all the way down. Always a little life left in it. And yet, and this is the wonder we'll spend the rest of our journey on, even though you can never reach the floor, you can get astonishingly, almost unbelievably close. Close enough for matter to change into something it has never been before. Think about how close. Let me try to give you the scale of it slowly, because the numbers here are the kind that lose their meaning if you say them too fast. We measure these tiny distances above absolute zero in fractions of a Kelvin, a thousandth of a Kelvin, a millionth, and then when the condensate first forms, we're talking about billionths of a Kelvin. There's even a word for it, a nanokelvin. 1 nanokelvin is a single billionth of a degree above the absolute floor of cold. The first Bose-Einstein condensate ever made lived at around 170 nanokelvin, 170 billionths of a degree above the bottom of the universe. Try to hold that number for a moment, not to grasp it exactly, but just to feel its smallness. If you took a single second and split it into a billion pieces, one of those slivers would be a nanokelvin's worth of cold. We're not talking about chilly, we're not talking about freezing, we're talking about a cold so extreme that it sits almost at the lowest temperature the universe will permit anything to have. And then it gets even more remarkable, which is the part I almost can't believe even saying it. By the year 2022, a team of physicists had pushed past nanokelvin entirely, down into picokelvin. A picokelvin is a trillionth of a degree. They reached, by some measures, around 38 picokelvin, 38 trillionths of a single degree above absolute zero. The coldest temperature, by some accounts, ever recorded anywhere, and we'll come to exactly how they did it much later tonight, because the way they reached it is so simple and so beautiful it almost makes you laugh. But for now, just let the number sit there, glowing softly in the dark. 38 trillionths of a degree above the lowest cold there is. Here is the part I want you to really feel, though, the part that to me is the heart of the whole thing. This coldest place, colder than the deepest dark between the stars, colder than anywhere we know of in the entire universe, colder than nature has ever managed to make anywhere on its own. This place was not found. It was built by people, by human hands, with patience and lasers and a great deal of care, inside a quiet room on Earth. The natural universe, for all its vastness, never gets this cold. Out in deep space, in the empty dark, the temperature hovers a few degrees above absolute zero. Cold beyond imagining, but nowhere near the floor. There are places where nature has done a little better. There's a wisp of gas out in the cosmos, a cloud called the Boomerang Nebula that drifts down to around 1 Kelvin, just 1 degree above the bottom. And that is the coldest natural place we've ever found anywhere in the heavens. The coldest spot in all of creation made by the universe itself. And a Bose-Einstein condensate in a lab is 1 billion times colder than that. So let that settle in gently as you breathe. The coldest spot in the known universe is not in some unreachable corner of the cosmos. It's here. It's on this planet. Right now, in laboratories, scattered across the Earth, in quiet rooms behind closed doors, there exist tiny clouds of matter that are colder than the void of space, colder than the dying breath of the most distant nebula, colder than anything nature ever made. And they were coaxed into being by ordinary people, working slowly and patiently with light and magnets and a kind of infinite gentleness. We didn't find the coldest place in the universe. We made it. Here, on Earth. There's something almost paradoxical about that, isn't there? You'd think the deepest cold would belong to the emptiest, loneliest, most remote places. The spaces between galaxies, the long, dark nowhere. And instead it belongs to a warm planet full of life and light, where someone in a lab coat decided to spend years learning how to slow atoms down until they came to rest. The coldest stillness in all of existence, born in the warmest, busiest corner we know. I keep coming back to that. It's a comforting kind of strangeness, the way the most extraordinary things can be made in the most ordinary rooms. Now, how on earth do you do it? How do you take a little cloud of atoms racing around at hundreds of meters per second, jittering with the warmth of the room, and slow them down, gently, without breaking anything, until they're moving so slowly, so faintly, that they sink down to a billionth of a degree above the absolute bottom of cold and merge into a single quantum wave? That's the great mystery of the mechanism, and it's the part most stories rush past, but we won't. We'll walk through it slowly because it's genuinely beautiful, and because the answer involves something you'd never guess. It involves slowing atoms down with light, of all things, with lasers that act like thick syrup. And it involves the very same physics that cools a cup of tea by your bedside. The ordinary made extraordinary again. But before we get to the how, we have to go back to the beginning of the whole idea, back to a year, 1924, when none of this could be done, when the cold required was unthinkable, unreachable, the stuff of pure imagination. Back to a quiet, almost forgotten letter that arrived on Einstein's desk, written by a little-known lecturer on the far side of the world. Because before anyone could ever make the fifth state of matter, someone first had to dream it. Someone had to do the strange and lonely thing of predicting, on paper, with nothing but mathematics, that if you could only get cold enough, colder than anyone in 1924 could imagine, matter would do something it had never been seen to do. And the strangest part of all, the man who predicted it was uneasy about his own prediction. He thought it so peculiar, so close to impossible, that he half doubted it himself. He set it down in the equations, and then he more or less set it aside, this curious consequence of his own mathematics, and the world set it aside too for a very long time. Decades would pass, the man would die, and still no one could prove him right, because no one could reach the cold. So let's go back there, slowly, to where the story truly begins. Let's go back to a paper that several journals rejected, and to the two men whose names would one day be joined forever to the coldest matter ever made. Let the room grow a little quieter. There's no rush. We have all the time in the world, and the whole long journey is still ahead of us. But before we walk into 1924, let me hold you here for just a moment longer in the present, in the wonder itself, because it's worth feeling the strangeness of the thing before we learn how it was dreamed. Picture it again. Thousands of atoms, each one its own tiny, restless thing, jittering, drifting, each keeping to itself the way a crowd of strangers in a station keeps to itself, everyone moving, everyone separate, nobody quite touching. That is matter as you have always known it. The chair beneath you, the blanket over you, the warm cup, if you have one nearby, all of it is countless separate particles, each one a private little island, each one doing its own restless dance. That is the rule. That has always been the rule. And then, in the coldest places human beings have ever made, the rule quietly breaks, because as you cool those atoms down past anything you have ever touched, down past the cold of ice, past the cold of dry ice, past the cold of liquid air, down and down toward a place so cold it has its own name, something begins to happen that has no everyday picture, no comfortable comparison, nothing in your kitchen or your garden that quite prepares you for it. The atoms stop being separate, they stop being a crowd, they begin slowly to overlap, to blur into one another, to forget, in a sense, that they were ever individuals at all. And at the coldest moment, thousands of them simply merge into a single, smooth, silent quantum wave. One thing, one coherent ripple of matter, behaving as a unit, moving as a unit, existing as a unit, a single superatom made of thousands. You could, in principle, take its picture. That is the part that still stops physicists in their tracks. The quantum strangeness that usually hides in the impossibly small, the behavior that normally lives far below anything you could ever see or photograph. In a Bose-Einstein condensate, it swells up to a scale you could put on a screen and stare at. The hidden becomes visible. The many become one. And it is, in the gentlest sense of the word, beautiful. So that's the wonder we're chasing tonight. Hold on to it. Let it sit somewhere soft in the back of your mind as we go. And while you settle in, wherever you are, whatever corner of the world is holding you right now, let me ask you something. The way I always do, where are you watching from tonight? What time is it where you are? Leave it in a comment if you feel like it, before you drift off. I love reading them. It's a quiet little map of all the places people are falling asleep to these same slow stories. And if you enjoy these slow journeys and you'd like more nights like this one, a gentle like and a subscribe really does help this sleepy little channel keep going. Small creators like me rely on it more than you'd think. And to those of you already subscribed, already here, already part of this, thank you. Truly. It means more than I can say. Now, settle in properly, let your shoulders drop. There is nothing you need to understand tonight, nothing you need to hold on to or remember. If you drift off somewhere in the middle of all this, and you very well might, that's perfectly all right. The ideas will still be here when you wake, patient as ever. We're going to move slowly through this, softly, one small mystery at a time, with no hurry and no test at the end. I'll try, as always, not to make it so interesting that it keeps you awake. Though if it does, well, at least you'll have learned something. A fair trade, I think. So let me set the scene properly. Let me tell you where this happens, because it's the part that I think is hardest to believe. It does not happen in deep space. It does not happen in some far-off nebula in the cold between the stars. It happens on Earth, in a room, a quiet, ordinary room, in an ordinary building with people in it wearing ordinary clothes, drinking coffee, checking instruments, talking in low voices, and somewhere in that room, inside a sealed chamber, smaller than you might imagine, human beings have built the coldest spot in the entire known universe. Colder than the darkest, emptiest void you could point to in the night sky. Colder than anything nature has ever managed anywhere in all the vastness we've ever looked at. A billionth of a degree above the absolute limit of cold, and then in time, a trillionth. Let those words land slowly because they're almost too small to feel. A billionth of a degree, not 1 degree, not a fraction of a degree, a billionth. And then colder still, but a trillionth, made by patient human hands, with light and with stillness, in a quiet room on this planet. There is something almost tender about that, isn't there? That the coldest, stillest place in all of creation isn't out there in the dark. It's here. We made it. We coaxed it into being, gently, on purpose. But to understand why that matters, Why a place that cold is so extraordinary? Well, we need to talk for a moment about the states of matter, about the different ways that the stuff of the world can arrange itself. Because the thing made in that cold room isn't just very cold matter. It is a different kind of matter altogether, a new state, a fifth state. You already know the first few. You've known them since you were a child, even if no one ever named them quite this way for you. There's solid, the ice cube, the stone, the wood of the table. Matter where the particles are locked together, holding their shape, refusing to flow. Steady, still, defined. There's liquid, the water, the tea, the rain on the window. Matter where the particles have loosened their grip on one another, where they slide and pour and take the shape of whatever holds them, but stay close, stay touching, stay together. There's gas. The air all around you right now, filling the room, filling your lungs as you breathe slowly in and slowly out. Matter where the particles have broken free of one another entirely, flying apart, spreading to fill whatever space they're given, restless and quick and invisible. And then there's a fourth, one you've seen even if you've never been told its name, plasma, the fire of a flame, the glow of a lightning bolt, the light of every star in the sky, the sun itself. Matter heated so fiercely that the atoms are torn apart, their electrons stripped away, a hot and charged and glowing soup. Most of the visible universe, in fact, is plasma. All those stars, all that light, solid, liquid, gas, plasma, 4 states, 4 ways for the world to be. And for a very long time, that was the whole list. That was matter in all its forms. But the 5th state isn't on that list because it isn't a hotter version of anything or a colder version of ice. It's something else. Something categorically different. The other 4 are mostly about how tightly the particles hold together or how violently they fly apart, about heat and motion and spacing. The 5th state is about something stranger. It's about the particles losing their separateness entirely, becoming one. It only appears at the very edge of cold, at temperatures the other 4 states never go near, and when it appears the rules quietly change. The atoms stop being a crowd and start being a single wave. That's why it earns its own place on the list. That's why it's a state all its own. And to make it, you have to go somewhere the universe almost never goes. You have to approach a place we call absolute zero. Let me tell you what that is, gently, because it's one of the loveliest ideas in all of physics. Everything around you all the time is moving, even the things that look perfectly still. The atoms in your blanket are trembling. The atoms in the wall are quivering in place. The molecules in the air are racing past your face at hundreds of meters per second, though you'll never feel a single one. And all of that motion, all that ceaseless, tiny jittering, that is what heat actually is. Heat isn't some substance that flows into things. Heat is motion. The faster the particles dance, the hotter the thing. The slower they move, the colder it gets. So imagine slowing them down. Imagine cooling something and cooling it more, and the particles moving slower and slower and slower still. Where does it end? What happens if you keep going? There is a bottom. There is a coldest possible cold, a temperature below which there is simply no further down to go, the point at which all that classical jittering, all that restless motion would finally come to rest. We call it absolute zero. And it sits at minus 273.15 degrees Celsius. Or, on the scale physicists prefer for exactly this reason, 0 Kelvin, the very bottom, the floor of cold. But here is the tender, almost poetic catch, and it's a real law of nature, not just a turn of phrase. You can never quite reach it. You can get close, impossibly, breathtakingly close, a billionth of a degree away, a trillionth of a degree away. But that final step, that last sliver of cold that would bring everything to a perfect and total stop, is forever just out of reach. There is a rule in physics called the third law of thermodynamics, and what it tells us in its quiet way is that absolute zero can be approached without end, but never actually arrived at. You can spend a lifetime and all your cleverness and all your light getting nearer and nearer, and you will always have just a little further you could go. And yet, even as we sit with that image, what is the floor of cold that can never quite be touched, the story doesn't stop there. Because someone, long before anyone had the tools to reach that floor, sat down and asked a different question. Not just how cold can things get, but what would happen if they got that cold? What strange, impossible thing might be waiting at the bottom? That someone was not working in a grand European laboratory. He didn't have the resources of a well-funded university physics department, the connections of the established scientific world, the colleagues who might take his stranger ideas seriously over coffee and chalk dust. He was a young lecturer at the University of Dhaka, in what was then the undivided Indian subcontinent, teaching physics to students in a city that was not yet a capital of anything much, and he was working, largely, alone. His name was Satyendra Nath Bose, and in the summer of 1924, Bose did something that would quietly reshape the way physicists understand the fundamental nature of matter. Though almost nobody realized it at the time, including, in some ways, Bose himself. He had been thinking about light, about the way light behaves when it is in thermal equilibrium, when it fills a closed cavity, bouncing around until it settles into a steady distribution across different energies and frequencies. There was already a law describing this discovered by Max Planck back in 1900, the blackbody radiation law. Planck's formula worked beautifully. It matched experiment almost perfectly. But the way Planck had derived it, and the mathematical path he had taken to arrive at it, involved a step that had always felt, to careful thinkers, slightly uncomfortable. A step that Planck himself had introduced somewhat reluctantly, without a fully satisfying justification. Bose thought he could do better. He thought he could derive the same result, the same correct formula, by starting from a cleaner, more principled foundation. And he did. But the method he used to get there contained something new, something subtle, something that, in his own telling, he might not have fully appreciated was new at all. Here is the essence of what he did, and it is worth sitting with slowly, because it is the kind of idea that sounds almost trivial when you state it simply, and yet opens into something vast. When you want to count how many ways you can arrange a collection of objects, the answer depends enormously on whether those objects are distinguishable from each other. Imagine you have 2 coins, and you want to count how many ways you can distribute them between 2 cups. If the coins are different, one is a penny and one is a dime, say, then there are 4 arrangements, both in the left cup, both in the right cup, the penny left and the dime right, or the penny right and the dime left. 4 possibilities, but if the coins are identical, truly identical, then 2 of those arrangements are the same. Penny left, dime right, and penny right, dime left. Those are no longer 2 different things. They're the same thing because the coins can't be told apart. So now there are only 3 arrangements, not 4. This sounds like a minor bookkeeping detail, a small matter of how you count. But in physics, how you count is everything. The statistics, the distribution of probabilities across different states, depends entirely on whether you treat the particles as distinguishable individuals or as genuinely, fundamentally identical. Classical physics had always treated particles as distinguishable. Even if 2 electrons, say, were in some sense the same kind of thing, you could imagine labeling them keeping track of which one was which. The counting methods of classical statistical mechanics were built on that assumption. What Bose realized, or perhaps stumbled into, or perhaps intuited more deeply than he articulated, was that light quanta, the packets of light energy that Einstein had proposed in 1905, were not like that. They were not distinguishable individuals. Two photons of the same energy were not just similar, they were genuinely, completely, physically identical. There was no label you could attach to tell them apart, because at a deep level there was nothing to tell apart. They were the same particle in the same way that two mathematical zeros are the same zero. When he counted the arrangements using this new logic, treating photons as truly indistinguishable, the formula that fell out was Planck's blackbody law. Exactly right. No uncomfortable assumptions required. He wrote it up carefully, this derivation, and sent it to a journal. The journal rejected it. He sent it elsewhere, rejected again. The work was new and it was correct, but the people reading it either didn't follow what was genuinely novel about it or didn't think the novelty mattered enough. So Bose did something slightly audacious. He wrote directly to Albert Einstein. Einstein was, by 1924, the most famous physicist in the world. He had the Nobel Prize from 1921, though awarded a year late in 1922. He had general relativity behind him, and the photoelectric effect, and the 1905 papers that had reshaped multiple branches of physics in a single year. And he was famously willing to read the letters of unknown correspondence if the physics was interesting. Bose's letter arrived, Einstein read it, and he immediately understood not only that Bose's derivation was correct, but that there was something fundamentally new inside it, something Bose had perhaps not even fully named. The new counting logic, the treatment of light quanta as truly indistinguishable, was not just a technical trick. It was a glimpse of a different kind of statistics, a different mathematical framework for describing how particles could be distributed across quantum states. Einstein translated Bose's paper himself, from English into German. He arranged for it to be published in the prestigious Zeitschrift für Physik, one of the leading physics journals of the day, with a note appending his own endorsement. Let that sit for a moment. One of the most celebrated scientists alive personally translating the rejected paper of an unknown lecturer in Dhaka and shepherding it into print. It is, if you let yourself think about it, rather a generous and beautiful thing. And it effectively launched Bose's international reputation, a reputation that would grow quietly and steadily through the rest of his long life. But Einstein didn't stop there, because as he was translating and thinking about Bose's work on photons, he began to wonder, what if you applied this same new statistics not to light, but to matter? Not to photons, which have no mass, but to actual atoms. In 1924 and then again in 1925, Einstein wrote two papers extending the logic. He took Bose's new counting framework and asked what it would predict for a gas of ordinary material particles, atoms, if those atoms were bosons, which is to say, if they obeyed this new kind of statistics. And what the mathematics told him was extraordinary. It was strange. It was, in Einstein's own words, and this is a direct reflection of his tone, something peculiar, a curious consequence, he called it. You can almost hear the slight unease in that word, peculiar, like he had followed the logic faithfully and arrived somewhere he wasn't entirely sure he believed. What the equations predicted was this. Below a certain critical temperature, a sudden dramatic thing would happen to the gas. A macroscopic fraction of all the atoms, not just a few, not a small percentage, but a large fraction, most of them, would simultaneously collapse into the very lowest possible quantum state, the ground state, the bottom rung of the energy ladder, all at once. Not because they were pushed there, not because something forced them, but because, according to the statistics, below that temperature it became overwhelmingly, statistically, mathematically inevitable. the system would spontaneously reorganize itself and a great crowd of atoms would pile into the same quantum state the way a crowd of people might suddenly all occupy the same thought, all humming the same note at the same moment, without any conductor. This is the Bose-Einstein condensate, the state itself. Einstein had predicted it in 1924 and 1925 from pure mathematical reasoning, following Bose's new statistics to their logical conclusion. And then he set it aside, not dismissively, but there was simply nothing to do with it yet. No one had any idea how to make something cold enough to test the prediction. The temperatures required were so far below anything achievable in any laboratory of the 1920s that the prediction felt, for practical purposes, like a thought experiment, a beautiful, peculiar thought experiment. It sat there in the journals, largely dormant, for decades. To understand why it would sit for so long, you need to understand something about the particles involved, because not just any particle can do what Einstein predicted. Not everything can pile into the same quantum state. Nature, in one of its sharper-edged rules, doesn't allow all particles to behave that way. Here is the division. Every particle in the universe, every electron, every proton, every photon, every atom, has a property called spin. Not spin in the literal sense of a ball rotating on an axis, though that image is sometimes used as a rough guide. Spin in quantum mechanics is a fundamental intrinsic property like charge or mass, and it takes specific, discrete values. Some particles have spin values that are whole numbers 0, 1, 2. We call these bosons. The photon is a boson. Certain atoms, depending on their total spin configuration, are bosons. Other particles have spin values that are half integers, 1/2, 3/2, 5/2. We call these fermions. The electron is a fermion. The proton is a fermion. Neutrons are fermions. Most of the matter you are made of, in the most direct sense, is made of fermions. And these two families obey completely different rules. Bosons, the particles named in honor of Bose, are sociable, gregarious, you might say. There is no limit to how many of them can occupy the same quantum state at the same time. If one photon is in a particular state, a second photon is, if anything, slightly more likely to join it there. Bosons actively want to be together. This is what makes lasers possible, the coherent pile-up of huge numbers of photons in the same quantum state. It is Bose-Einstein statistics at work in your laser pointer. Fermions are the opposite. They are fiercely, absolutely, non-negotiably antisocial. No two fermions can ever occupy the same quantum state at the same time. If one electron is in a particular state, a second electron is prohibited, not discouraged, not unlikely, but physically forbidden from occupying that same state. This rule has a name. It is called the Pauli exclusion principle, after Wolfgang Pauli, who formulated it in 1925, and it is the reason matter has structure. It is the reason atoms have size and shape, the reason electrons occupy different shells and orbitals, the reason chemistry is possible at all. If electrons were bosons, every atom would collapse into its lowest energy state, and the rich architecture of the periodic table would cease to exist. The other family is named for Enrico Fermi, the Italian physicist who developed the parallel statistical framework for half-integer spin particles. Fermi-Dirac statistics, the mathematics of the antisocial particles, is what governs the behavior of electrons in a metal, the properties of white dwarf stars, the quantum structure of atomic nuclei. Fermions follow Fermi, and bosons follow Bose. And the two behaviors are as different as anything in physics. What this means for Bose-Einstein condensation is clear. It can only happen for bosons, because BEC is precisely the phenomenon of many particles piling into the same quantum state. And fermions refuse to do that, no exceptions. You cannot make a Bose-Einstein condensate out of electrons. You cannot make one out of protons. You can only make one out of particles whose spin follows the whole number rule. Rubidium-87, the atom Eric Cornell and Carl Wyman would eventually use, is a boson. Its total spin, adding up the contributions from its electrons, protons and neutrons, comes out to an integer, which places the whole atom in the boson category. Sodium-23, which Wolfgang Ketterle would use, is also a boson, not by accident. The experimenters chose their atoms carefully. Now here is something worth pausing over because it illuminates a kind of historical sequence that is easy to miss if you think of physics as a clean march of progress. Einstein wrote down the prediction of Bose-Einstein condensation in 1924 and 1925. But at that same moment, right in that very same window, the edifice of quantum mechanics, as we now know it, was being built. Werner Heisenberg published his matrix mechanics, the first complete formulation of quantum theory, in 1925. Erwin Schrödinger published his wave equation in 1926. The uncertainty principle came in 1927. All of that, the mathematical framework that would eventually explain why and how atoms have wave functions, why quantum states work the way they do, why the de Broglie wavelength swells as particles slow, all of it came after Einstein's prediction of the condensate. Einstein predicted the thing before the theory existed that would fully explain it. He predicted it from statistical reasoning alone. He knew that the mathematics of Bose's counting produced this strange clustering at low temperatures, and he trusted the mathematics even though the deeper physical picture, the waves, the wave functions, the geometry of quantum states, was still being assembled by other people in other rooms. It is a little like predicting the sound a new instrument would make before anyone had built the instrument or written down the physics of acoustics. Pure statistical inevitability carried to its logical end. And Satyendra Nath Bose himself, the man who started this chain, the man whose name is on both the statistics and the particles and the condensate, he never received the Nobel Prize. This is noted frequently and always with a tone of something unsettled. The boson is named for him. The statistics bear his name. The condensate carries his name. Three things in the living vocabulary of modern physics, and not one of them came with the prize that physics hands out to say, yes, this matters, we knew it mattered, we said so at the time. He continued his career teaching and researching in India. He was respected, internationally recognized, appointed to positions of honor later in his life. But the Nobel, which arrived for Cornell, Wyman, and Ketterle when the condensate was finally made in the laboratory, never came to Bose. He died in 1974, 21 years before the thing he helped predict was first held in a laboratory trap. History sometimes keeps its debts in silence. But even as the theory sat quietly in the journals through the 1930s and 1940s and 1950s, something else was happening. Something that, in retrospect, was a signal. A clue that the Bose-Einstein prediction was not merely a mathematical curiosity, but a real physical phenomenon waiting to emerge wherever the conditions allowed. It happened with helium. Helium is the lightest of the noble gases, chemically inert, colorless, odorless. At ordinary pressures, it refuses to become a solid even at the coldest temperatures. It stays liquid, the only element that does this, held liquid by the quantum jittering of its atoms, which are so light that even near absolute zero they can't quite settle into a fixed, crystalline arrangement. In a way, helium is the most quantum of all the everyday substances, its behavior shaped by quantum mechanics in ways that other liquids and solids simply aren't. In 1937, something extraordinary was observed in liquid helium-4, below a certain temperature, a temperature given a name because of the shape of a graph, the lambda point, at 2.17 Kelvin. Helium-4 undergoes a phase transition into a state called a superfluid. And a superfluid does something that fluids are not supposed to do. It flows with zero viscosity. no friction, none. A regular fluid, water, oil, even liquid nitrogen, has some internal resistance to flow, some stickiness that dissipates energy when it moves. A superfluid has none, not a tiny amount, exactly zero. It flows through tiny openings without slowing. It flows over barriers without resistance. And most famously, most hauntingly, most visibly, it climbs. A container of superfluid helium placed inside a slightly warmer outer container will slowly climb the walls of the inner container, crawl over the rim, and drip down the outside, up the wall, against gravity. It does this because the quantum mechanical flow has no friction to stop it, and the film of superfluid on the wall is thin enough to be dragged upward by the weak molecular forces at the surface. It climbs because nothing stops it. When physicists first observed this, it was 1937, and it was genuinely shocking. Liquids do not do this, and the explanation, worked out slowly and carefully over the following years, pointed directly to something like Bose-Einstein behavior. Helium-4, it turned out, is a boson. Its atoms have integer spin. Below the lambda point, a significant fraction of the helium atoms condense into a single quantum state, not a pure, gaseous BEC, because helium is a liquid, and the atoms interact strongly with each other, not the dilute ideal gas Einstein had imagined, but something deeply related to it, something that carried the same essential physics. The superfluid was a ghost of the condensate, or perhaps the condensate was a purified, idealized version of the superfluid. Either way, the behavior of liquid helium-4 below 2.17 Kelvin was a clue, readable in retrospect, that Einstein had been right in 1925. That the mathematics really did describe something real. That matter, in the right conditions, could stop being a collection of individuals and become something closer to a single entity. It was not what Einstein had predicted exactly. It was messier, more complex, modified by the strong interactions between helium atoms that a simple gas doesn't have. But it was family. It belonged to the same physics. And it was the first hint, the first observable, reproducible, measurable hint, that Bose-Einstein condensation was not a mathematical fiction. It would take almost 60 more years to make the clean, ideal version. But helium, climbing its container walls in a cryogenics laboratory in 1937, was whispering that it was possible. There is something almost meditative about the image of superfluid helium creeping silently up the walls of a cold glass container. No noise, no effort, no resistance. It simply goes because nothing prevents it, because the quantum state it occupies knows no friction, because the many atoms have become in some sense a single thing, moving together, obeying one wave function rather than many, their individual identities dissolved into a collective flow. And there in that quiet image is the thing that would eventually be made fully real in 1995 in a laboratory in Colorado, using laser light and magnetic fields and the same physics that cools a cup of tea. Though we'll come to all of that in time. For now, stay with this. A young man in Dhaka in 1924 rederiving a formula about the way light fills a closed room, and discovering, almost as a byproduct, a new way to count, a new mathematics of identity, and Einstein reading the letter, translating it by hand, and following the logic out to its strange and peculiar end, to a prediction that matter itself, cooled to a depth that seemed almost unreachable, would collapse into a single shared state. Bosons piling together without limit, fermions held apart by a law that has no exceptions, and somewhere between these two behaviors, sitting at the heart of the distinction, the question of what it means for two things to be truly identical. Not just similar, not just the same in all their measurable properties, but identical in the way that makes them, at a mathematical level, one and the same. That question is so abstract, so philosophical, so easy to dismiss as wordplay, turns out to have physical consequences you can see. You can observe them in a climbing film of cold liquid on the inside of a glass container. You can observe them in the interference of two condensates when they overlap and produce ripples in their density, the way two pebbles dropped in still water produce ripples in theirs. You can observe them in the sharp spike of a false color image taken in a Colorado laboratory on the 5th of June, 1995, showing thousands of atoms all suddenly sharing the same velocity, the same state, where a moment before they had been a warm blur of individuals moving in different directions. But all of that still required one more thing. It required someone to figure out how, actually and practically and physically, to make something cold enough, not theoretically cold, not approaching cold on a graph, cold, a billionth of a degree above the floor. And that meant solving a problem that had no clean answer when Einstein wrote his papers in 1924 and 1925, because the tools to solve it didn't exist yet. The tools would take another 70 years to invent, and when they came, they were made of light. There is a satisfying irony in this if you're in the right frame of mind to appreciate it. The story begins with Bose's paper about light, about photons, about how light fills a cavity, about the statistics of light quanta. And the method that finally allowed physicists to reach the temperatures needed to create the condensate was built almost entirely out of light, out of lasers aimed with great care at small clouds of trapped atoms, doing something that seems almost paradoxical at first glance, using light to cool things down. This needs a little unpacking because it runs against the usual intuition. Light from the sun warms you. Light from a lamp warms a room. How could light possibly cool an atom? The answer lives in the Doppler effect and in the way atoms absorb photons. When an atom absorbs a photon, it gets a tiny kick, a tiny push in the direction the photon was traveling. The momentum of the photon gets transferred to the atom. This is a real, measurable thing. It is the same physics, scaled down enormously, as the light pressure that is used to push spacecraft with solar sails. Photons carry momentum, and when they hit an atom and are absorbed, that momentum goes somewhere. Now imagine an atom moving through space, drifting, say, toward you, toward the source of a laser beam you've aimed at it. In the frame of the atom, the laser light looks slightly blue-shifted, slightly higher frequency than it actually is because of the Doppler effect, because the atom is moving toward the source. If you tune the laser to a frequency just slightly below the atom's natural absorption resonance, the frequency it would most naturally absorb, then when the atom is moving toward the laser, the Doppler blue shift brings the light right into resonance, and the atom absorbs a photon and gets a tiny kick backward, a tiny push opposing its motion. When the atom is moving away from the laser, the light is redshifted, falls out of resonance, and the atom absorbs far fewer photons and gets far fewer opposing kicks. The result is that atoms moving toward the laser are preferentially slowed. They absorb more photons when they're moving toward the beam, and each absorption pushes them back. Now do this from 6 directions simultaneously, 6 laser beams aimed at the atoms from all sides, top and bottom, left and right, front and back. Any atom moving in any direction will be moving toward one of the beams, and it will be slowed by it. The atoms, no matter which way they're drifting, keep getting nudged, gently but persistently, back toward stillness. The physicists who developed this technique gave it a name that immediately makes you feel it rather than just understand it. They called it optical molasses, because that is what it is like for the atoms. They are trying to move through it, and it resists them from every direction, the way molasses resists a spoon. Every time an atom tries to go somewhere, a laser beam is there, nudging it back. The atoms wade through the light and slow down, and the temperature of the cloud drops. It is extraordinary when you hold it in mind, using beams of light to turn a cloud of atoms into something like a very cold, very still, very thin gas, slowed down by the gentle, persistent pressure of tuned photons. Not by a refrigerator, not by a compressor, by light. The technique and related methods of laser cooling earned the 1997 Nobel Prize in Physics, shared by three physicists, Stephen Chu, Claude Cohen-Tanuji, and William Phillips. Three people working somewhat independently who each contributed pieces of the understanding and practice that made laser cooling a real experimental tool. Their work didn't just open the path to Bose-Einstein condensation. It opened an entire era of cold atom physics, one that is still unfolding in laboratories around the world tonight, right now, in rooms full of equipment and vacuum chambers and laser light, while the people who built them have gone home to sleep. But optical molasses, remarkable as it is, could only go so far. The atoms, cooled by laser light, could be brought down to temperatures in the range of microkelvin, millionths of a Kelvin, above absolute zero, genuinely frigid by any everyday standard, but not quite cold enough. The critical temperature for Bose-Einstein condensation in the dilute atomic gases Cornell and Wyman were working with sat even lower, in the range of nanokelvin, billionths of a Kelvin. They needed to go further. And the method they used to cross that last gap is something you encounter every single day of your life, without usually thinking about it in quite these terms. Evaporative cooling. When you make a cup of tea and leave it sitting on the table, it cools. You know this. But think carefully about why. The water molecules in your tea are moving at a range of different speeds. A distribution, not all the same. The fastest, hottest molecules at the surface have enough energy to escape the liquid entirely. They evaporate, they leave. And when they leave, they carry their energy away with them. And the average energy, that is the average speed, the temperature, of the molecules left behind drops. The remaining tea is colder because the hottest members of the collection have departed. Your tea cools itself by losing its fastest molecules to the air. Cornell, Wyman, and their colleagues applied exactly this logic to their cloud of laser-cooled atoms, but with a precise and controllable mechanism rather than a teacup and an open room. The laser-cooled atoms were held in a magnetic trap, a carefully shaped magnetic field that kept the atoms confined in a small region of space like an invisible bowl. The magnetic field can only trap atoms in certain spin states, and the trap has, in effect, walls. Magnetic walls which the hotter, faster atoms have enough energy to surmount and escape over. The cooler, slower atoms don't have enough energy to reach the walls. They stay inside. The trick is to gradually, patiently lower the walls, to adjust the magnetic field so that its confining strength slowly decreases and the threshold energy needed to escape slowly drops. This lets progressively colder and colder atoms escape, not just the very hottest ones, but the next tier of hot ones, and then the next. Each time atoms escape, the remaining cloud rethermalizes. The remaining atoms share their energy around and settle to a new, lower temperature. And then the walls come down a little more. And the remaining atoms are colder still. And the walls come down again. And so on, down and down, following the temperature into depths that laser cooling alone could never reach. Each round of evaporation takes the last of the more energetic particles away, and what remains is colder and colder and more still and more still. The atoms that survive to the end of this process are the quietest ones. The ones with almost no motion left. This is evaporative cooling, the physics of a cooling teacup applied to a cloud of atoms in a magnetic trap, in a vacuum chamber, inside a laboratory, taken to a billionth of a degree above zero. It is the same physics in the end, the same gentle logic by which a hot thing sheds its restlessness. Your tea cools on the nightstand because the fastest, most energetic water molecules escape as steam, and the ones that remain behind average out to something quieter. The rubidium atoms in that magnetic trap cool because the fastest, most energetic atoms among them, the ones with the most motion, the most urgency, climb over the magnetic walls and escape into the vacuum, and the ones that remain average out to something quieter still. There is a kind of beauty in how the same principle operates at such wildly different scales. Your tea, a few degrees above room temperature, cooling by tens of degrees over the course of an evening. A cloud of rubidium atoms, already cold beyond almost any point in the natural world, cooling by nanokelvin, by billionths of a degree, over the course of a few long, patient seconds in a laboratory in Colorado. The mechanism is the same. The arithmetic of escape and remainder. The physics of what stays and what goes, but the outcome in that laboratory is something your teacup never approaches. Let's stay with the mechanism for a moment longer, because it really is worth understanding slowly. At the temperature laser cooling can reach a few millionths of a degree above absolute zero, a few microkelvin. The atoms in the trap are moving, but barely. They are not the frantic, fast-moving particles of room temperature air. They are slow, almost still. But almost still is not the same as still. There is motion remaining, restlessness. The atoms are still individuals, each pursuing its own private path through the trap, each with its own velocity, its own direction, its own small share of kinetic energy. They have been slowed, but they have not yet been made into something new. For that, the evaporation has to go further. The walls have to come down lower and lower and lower. The threshold has to drop until only the very quietest atoms remain, until almost all of the motion has been shed, until the atoms in the remaining cloud have so little kinetic energy that the concept of individual motion starts to lose its meaning. And here is where something remarkable begins to happen. Something that has nothing to do with temperature in the ordinary sense and everything to do with the quantum nature of matter itself. Every particle in the universe, every electron, every proton, every atom has a size. Not the size of its nucleus, not the size you might imagine if you pictured a tiny, hard sphere. A quantum mechanical size, a kind of spread or smear, built into the nature of the particle by quantum mechanics, and this size is described by what physicists call the thermal de Broglie wavelength. It is a name that combines a few ideas, and it is worth unpacking each of them quietly. Louis de Broglie was a French physicist who proposed in 1924, the same year Bose and Einstein were working out the statistics of bosons, that every particle of matter has an associated wave. Just as light, which had been understood as a wave, was found by Einstein to also behave as a particle, the photon, de Broglie proposed that particles of matter, electrons, atoms, anything with mass, also have a wave nature. The wavelength of this wave depends on the particle's momentum. The heavier and faster the particle, the shorter the wave, the lighter and slower the longer. A room temperature atom moves fast. Its de Broglie wavelength is extremely short, shorter than the diameter of the atom itself, shorter than the spacing between atoms in a gas. You would never notice it. You would never see any quantum wave effects because the wavelength is too tiny, too fine-grained to make itself felt at the scale of the atom's interactions with each other. But slow the atom down, cool it, take away its kinetic energy. As the atom moves more and more slowly, its de Broglie wavelength grows longer. The wave spreads, the quantum smear extends, the atom's quantum mechanical presence stretches out into the space around it. Picture it like this. Imagine the atom as something like a ripple on water. When it is hot and fast, it is a very tight, compact ripple, smaller than the space between it and its neighbors. The ripples don't overlap. Each atom is effectively a separate thing, with its own private ripple going its own private way. At those temperatures, the atoms don't notice each other's wave nature. They just collide like tiny billiard balls, classical objects more or less. But as you cool them down, as you slow them with laser light and then strip away the fastest among them with evaporation, those ripples begin to spread. The de Broglie wavelengths grow longer and longer. And at some point, in that descending quiet of a nano-Kelvin trap, the wavelengths become comparable to the spacing between the atoms themselves. At that moment, the ripples start to overlap. And when quantum waves overlap, they do what waves do. They interfere, they mix, they influence each other. They begin to lose the quality of being separate things. The boundaries between one atom's wave and the next start to blur. Now lower the trap walls a little more. Let a few more of the fastest atoms escape. The cloud grows colder still. The wavelengths grow longer still. The overlap deepens. The interference strengthens. And then, at some precise critical temperature, for rubidium-87 in a trap at the density Cornell and Wyman were working with, at around 170 nanokelvin, something crosses a threshold. The wavelengths have grown long enough and the overlap has become complete enough that the atoms can no longer be described as separate waves at all. They have merged. The many individual wave functions have collapsed into a single shared wave function, a single coherent quantum entity. This is the Bose-Einstein condensate. The atoms haven't fused in a nuclear sense, they haven't combined chemically. Their nuclei are still distinct, still rubidium, but in a quantum mechanical sense they have ceased to be separate. They are now one system described by one wave function, occupying one quantum state, the very lowest energy state available to them. They have all simultaneously fallen to the bottom of the quantum ladder and come to rest there together. Physicists sometimes call it a superatom, not because it is one large nucleus, but because thousands of separate atoms are now behaving as if they were a single quantum object, a single coherent wave of matter that you could, in principle, see, or at least photograph in its velocity distribution if you had the right detector. And that is what makes it the fifth state of matter, and not merely a very cold version of one of the other four. A cold solid is still a solid. The atoms are ordered, yes, locked into a crystal lattice, barely vibrating, but they are still separate. Each sodium atom in a grain of salt is still a distinct quantum entity, distinct from its neighbor, distinct from the one across the lattice. They share a structure, but they don't share an identity. A cold gas is still a gas. Atoms moving, bouncing, occupying a wide range of quantum states, each of them an individual. A very cold gas is still that, until, all at once, it isn't. The Bose-Einstein condensate is distinct not in degree but in kind. The atoms in a beck are not just slowed down, they are unified. They are no longer a population of individual particles in different quantum states. They are all in the same state, not similar states, the same one. That is the thing that crosses a categorical line, and it is only possible for bosons. This is worth coming back to quietly because it is the key to everything. Bosons, particles with integer spin, are allowed, by the laws of quantum mechanics, to occupy the same quantum state without limit. You can pile as many bosons as you like into the single lowest energy state. Nothing prevents it. Nature permits it. In fact, once a few bosons occupy a state, quantum statistics makes it more likely that others will follow. The state fills and goes on filling. That is what happens in the Beck. Fermions, particles with half-integer spin like electrons and protons, are forbidden from this. The Pauli exclusion principle, named for the Austrian physicist Wolfgang Pauli, says that no two identical fermions can occupy the same quantum state simultaneously. This is why atoms have electron shells, why matter takes up space, why the world has structure and solidity. Fermions refuse to share, they insist on their individuality, they maintain their separateness. Bosons have no such insistence. Given the right conditions, given cold enough temperatures, given the right kind of atom, bosons will pool into a single state, willingly, even eagerly. The mathematics of boson statistics makes it inevitable, and this is why the atoms that Cornell and Wieman used were rubidium-87 and not, say, a cloud of electrons. The rubidium-87 atom, as a whole, nucleus plus its electrons, has an integer total spin. It is, therefore, a boson. Sodium-23, the atom kettle used at MIT, is also a boson. Lithium-7, used in other early experiments, a boson. The right atoms for the job are the ones whose quantum accounting comes out to an integer spin, so that nothing in the laws of physics objects to all of them settling into the same quantum home. It is a quiet fact that the difference between a world of structure and a world of perfect, uncanny unity comes down, in the end, to whether a particle's spin adds up to a whole number or half of one. Now, the condensate has formed. Thousands of rubidium atoms in a magnetic trap inside a vacuum chamber at the University of Colorado in Boulder have merged into a single quantum wave. What does it actually look like? Not like much to casual observation. The condensate is tiny. A cloud of around 2,000 atoms at 170 nanokelvin occupies a region perhaps 1/10 of a millimeter across. Small, but not invisible. What Cornell and Wieman saw on the 5th of June in 1995 was the result of a measurement technique standard in cold atom physics. They switched off the trap and let the atoms expand freely, and then took a photograph using absorption imaging, measuring the shadow the atoms cast when illuminated by a resonant laser beam. The image they got was not a photograph of the atoms in the ordinary sense. It was a velocity distribution map, a picture of how fast the atoms were moving, which direction, and what appeared in that image became one of the most reproduced figures in physics of the late 20th century. Before condensation, the velocity distribution is broad and smooth. The atoms are moving in all directions with a range of speeds, and the distribution of those speeds is the familiar bell-curved shape of a thermal cloud. Atoms with low velocity in the middle, atoms with high velocity out toward the edges, a gentle rounded mound in the data, and then as the temperature drops through the transition, something appears at the center. A spike. A sharp, narrow peak, rising directly from the middle of the broad thermal mound like a needle of cold glass emerging from the warm fog. That spike is the condensate. Those are the atoms with essentially zero velocity. Not zero temperature. That cannot be. The third law of thermodynamics will not permit it. But zero velocity to the precision available. Atoms that have all collapsed into the lowest quantum state and carry with them, to the measurement, no residual directed motion above the quantum noise. The peak grows as the temperature drops further. More and more atoms fall into the condensate. The thermal background remains, surrounding it, but shrinks as a fraction. The spike dominates. This image, this sharp peak emerging from its thermal cloud, is the signature of Bose-Einstein condensation. It is the visual fingerprint of the fifth state of matter coming into being. And the moment Cornell and Wieman saw it, they knew. It took roughly 2 hours of cooling and preparation to produce each condensate, and then it existed, this fragile, unified quantum thing, for a fraction of a second before the atoms drifted away from each other and the condensate dissolved. And then the experiment was reset, and the cooling began again, and the condensate was made again, and the measurement taken again and again and again in that quiet laboratory. The same journey, from room temperature down to laser-cooled microkelvin, then down through the long patience of evaporation to 170 nanokelvin, and the spike appearing in the distribution, and then gone, and then again. For a moment, let's stay with the fragility. A Bose-Einstein condensate is, in one sense, the most orderly matter in existence. All the atoms are in one state. There is no thermal disorder, no random jumble of velocities, no chaos at all. It is quantum perfection, or as close to it as anything in the physical universe ever gets. And yet it is also the most delicate thing in existence. A single molecule of room temperature air, if it wandered into the trap, would carry enough energy to smash through the condensate the way a warm hand passing through a soap bubble destroys it. The atoms of the condensate would scatter, heat, lose their coherence, become individual again. The condensate would vanish in an instant. This is why the experiment requires an ultra-high vacuum. Not just a good vacuum, an ultra-high vacuum, a near-perfect emptiness, where the pressure is 1 trillion times lower than the atmosphere outside your window. At those pressures, stray air molecules are so rare that the condensate can survive for seconds, sometimes longer, without being struck. A few seconds of existence, enough time for a measurement, a photograph, an observation, and then gone. The diluteness of the condensate itself is, when you sit with it, one of the more quietly astonishing things about it. The atoms in that magnetic trap, those 2,000 rubidium atoms in their 1/10 of a millimeter cloud, are far apart from each other by atomic standards. The density of a Beck is typically 100,000 times less than the density of ordinary air. The atoms have plenty of room, they almost never touch. And yet, despite that emptiness, despite being a cloud so thin it would make a decent vacuum in its own right, these atoms have become the most ordered matter in existence. Their quantum waves have merged, their identities have dissolved into a collective, not because they are crowded together and forced into proximity, but because they are so cold that their quantum natures extend far enough to find each other anyway. This is one of the things that makes cold physics feel to me like a kind of quiet miracle. The atoms are barely there, scattered across a near vacuum, and yet they are, at the quantum level, completely entangled in their oneness, dilute and unified, empty and perfectly ordered. The two things that seem like they should exclude each other and don't. Evaporative cooling, the physics of the teacup taken to 1/1000th of a degree, is what bridges the gap between laser-cooled microkelvin and the condensate transition. But it does not work alone. The atoms have to be held during the evaporation. They have to be contained in a region of space while the process proceeds without any container walls of the ordinary kind, because ordinary walls would be warm, and warm walls would heat the atoms back up instantly. This is where the magnetic trap comes in, and the optical dipole trap. The magnetic trap works by exploiting the fact that atoms in certain quantum states experience a force in a magnetic field, a force that either pushes them toward the strongest part of the field or away from it, depending on the state. Cornell and Wyman used a trap design called a time-orbiting potential trap, or TOP trap, which uses a combination of magnetic fields to confine atoms in the low field-seeking state, holding them in a tiny region of space with no material walls at all. Just shaped magnetic fields, invisible walls. The atoms bounce around inside this invisible bowl, and when they are energetic enough to reach the edge of it, they change state and are no longer trapped, and they fly away. The trap lets them go. The cooler atoms, who can't reach the edges, stay. The magnetic trap is elegant in its minimalism, no solid surfaces, no material container. Just the atom's response to the geometry of a magnetic field exploited to hold a cloud of matter at the threshold of absolute zero. There is also the optical dipole trap, used in many experiments either alongside or instead of the magnetic trap. In an optical dipole trap, Focused laser light creates an intensity gradient, a place where the light is brightest at the center. Atoms responding to the oscillating electric field of the laser are drawn toward the region of highest intensity and held there. Again, no walls, no container, no material boundary. Just the force the light itself exerts on the atoms, a trap made of light holding matter at the coldest temperatures in the universe. It is, I think, one of the more beautiful ironies in experimental physics that to cool atoms using light, as laser cooling does, and then to contain them using light, as the optical dipole trap does, you are using something that moves at the fastest speed in the universe to produce the slowest, stillest matter in the universe. The same phenomenon, pointed two ways. Speed making stillness. Light making cold. The laser cooling that precedes the evaporation is itself a piece of work worth lingering over because the way it slows atoms is subtle and lovely. The technique exploits the Doppler effect. You know the Doppler effect as the reason a passing ambulance's siren changes pitch as it goes by. As the ambulance approaches, the sound waves ahead of it are compressed. The frequency is higher, the pitch is higher. As it moves away, the sound waves behind it are stretched. The frequency is lower, the pitch drops. It is not that the siren changes, it is that the motion of the source shifts the frequency you receive, depending on your relative motion. The same thing happens with light. If an atom is moving toward a laser beam, the light waves of the beam are slightly compressed from the atom's point of view. The frequency is slightly shifted upward toward the blue end of the spectrum. If the atom is moving away from the beam, the frequency is shifted slightly downward toward the red. Now, atoms absorb light only at specific frequencies. Their resonant frequencies determined by the energy structure of their electrons. Like a tuning fork that only resonates when struck at its natural frequency. In laser cooling, the laser is tuned to a frequency just slightly below the atom's resonance frequency, slightly red detuned in the language of the field. Most atoms, most of the time, find this laser light slightly off frequency and ignore it. But an atom moving toward the laser beam experiences that slight upward Doppler shift, and suddenly the laser frequency, blue shifted by the atom's motion, matches the resonance. The atom absorbs a photon, and when an atom absorbs a photon, it receives a tiny kick, a tiny push in the direction the photon was traveling, which is precisely the direction the atom was moving from, toward the laser. The atom absorbs the photon, and the photon's momentum pushes back against the atom's motion. It is slowed slightly by each absorption. Then the atom re-emits the photon in a random direction and returns to its ground state, and it can absorb again and be slowed again and again and again. 6 laser beams in an optical molasses setup are pointed at the atom cloud from all 6 directions: up, down, left, right, forward, back. No matter which way an atom moves, it runs into a laser beam and preferentially absorbs from it, because the Doppler shift makes that particular laser closer to resonance. The atom is always being pushed back from every direction. It is as if the atoms are moving through a thick, invisible syrup, resisted whichever way they go, slowed in every direction simultaneously, their velocities bleeding away into the absorbed photons, into the light. Optical molasses. That is the name the physicists gave it, and it is apt. The atoms wade through laser light the way your arm wades through water, slowed by the resistance, their motion consumed. The technique was developed in the 1980s by 3 physicists who would share the 1997 Nobel Prize in Physics for it: Stephen Chu, who was then at Bell Labs and Stanford, Claude Cohen-Tanuji at the École Normale Supérieure in Paris, and William Phillips at what is now NIST, the National Institute of Standards and Technology. Each of them approached the problem from a slightly different angle, developed techniques that complemented and extended each other's work, and together they brought the field of laser cooling to the point where temperatures of a few microkelvin, a few millionths of a degree above absolute zero, became routine. Routine is a funny word for it. A few microkelvin, millions of times colder than the inside of your freezer, hundreds of times colder than liquid nitrogen, cold enough that the atoms move at meters per second rather than hundreds of meters per second. Slower than a fast walk. Remarkable by any ordinary measure. And not yet cold enough, because the condensate forms at nanokelvin, billionths of a degree. Laser cooling gets you to microkelvin, millionths of a degree. There is still a factor of 1,000 to go in temperature before the condensate transition. That factor of 1,000 is what evaporative cooling provides. That is the bridge. So the sequence in a Beck experiment is this. First, you load the atoms from a hot source, a small oven, or a background gas, or a source of rubidium vapor, into a magneto-optical trap. A magneto-optical trap combines laser cooling with a shaped magnetic field, and it can capture a large initial cloud of atoms at around a millikelvin, 1,000th of a degree, and hold them. This is still hot by the standards of what comes next, but it is a manageable starting point. Then the cooling lasers refine the temperature further. Optical molasses, sub-Doppler cooling techniques that push below what simple Doppler arguments would suggest. Techniques that Chu, Cohen, Tanucci, and Phillips also developed bring the cloud down to the microkelvin range, a few millionths of a degree above absolute zero. Then the atoms are transferred into the magnetic trap or the optical dipole trap, or some combination of the two. The laser cooling switches off, because at nanokelvin temperatures, the tiny random kicks from photon re-emission would actually heat the atoms slightly rather than cool them. The trap takes over, and then the evaporation begins, patient, slow, methodical. The walls of the trap are lowered, a little at a time. The hottest atoms escape. The remaining cloud cools. The walls are lowered again. The process takes seconds, sometimes tens of seconds, depending on the geometry and the atom species and the density of the cloud. Down through nanokelvin, the atoms slow. The de Broglie wavelengths stretch, the quantum waves extend, the overlap grows, until at a specific temperature, or the critical temperature for that particular atom, at that particular density, the threshold is crossed. The wavelengths become comparable to the interatomic spacing. The separate wave functions merge, the condensate forms, and the spike appears in the velocity distribution. 2,000 atoms, give or take, in the case of Cornell and Wyman's first condensate, at 170 nanokelvin, in a trap so small and so cold and so isolated from the room around it that the room might as well not exist. And then it is gone. Seconds. The atoms drift, the trap is switched off for measurement, the condensate dissolves, the data is recorded, and the experiment begins again. It takes, when you add it all up, an extraordinary amount of careful engineering just to produce those few seconds of condensate. The vacuum system, pumped to a pressure of around 10 to the minus 11 torr, 100 billion times less than atmospheric pressure, must be maintained with constant effort. The magnetic coils that shape the trap must be driven with precisely controlled currents. The lasers, which must be locked to specific frequencies, stable to parts per billion, require their own elaborate control systems with feedback loops watching the laser's frequency continuously and correcting any drift. The whole apparatus, a typical BC machine, fills much of a laboratory table, racks of electronics, optical components, mirrors, lenses, beam splitters, acousto-optic modulators, all aligned with micrometer precision, computers that monitor and control every stage of the cooling sequence, from the initial atom loading through the evaporation ramp to the final measurement. And at the center of all of it, a small glass chamber a few centimeters across, pumped to near-perfect emptiness. Inside that chamber, a tiny, invisible cloud of atoms hanging in the intersection of laser beams and magnetic fields, growing colder and colder until, for a few seconds, it becomes the coldest, most perfectly ordered matter in existence. And then the next run begins. Cornell and Wyman ran their experiment many times before they were certain they had made a condensate. Condensation is not always obvious from a single data run. You have to see the spike appear at the right temperature, watch it grow as you push the temperature lower, confirm that its shape matches the theoretical expectation for a condensate rather than a very cold thermal cloud. They worked through the data carefully, patiently, and when they were certain, in June of 1995, they reported the result. The response from the physics community was immediate and enthusiastic. The prediction that had sat dormant since 1924, that had waited through the birth of quantum mechanics, through the entire history of nuclear physics and particle physics and cosmology, had finally been tested and confirmed. 71 years. And the atoms that had been used were not exotic. Rubidium-87, an alkali metal, the kind of element that sits in the first column of the periodic table, with one loosely held outer electron, easy to handle with laser light, easy to trap. Available. Ordinary by the standards of atomic physics. The extraordinary result had been achieved with ordinary materials in an ordinary, if extremely well-equipped, laboratory, by physicists working patiently through an engineering problem that had taken a decade of gradual progress to solve. The patience of that decade deserves acknowledgement. Cornell and Wyman didn't arrive at the BEC overnight. The techniques they used, the magneto-optical traps, the evaporative cooling, the specific trap geometry, were developed over years, refined by many groups in a community-wide effort that is less dramatic than a single, heroic discovery, but more representative of how physics actually works. Many people contributed ideas and techniques. Cornell and Wyman assembled the right combination, in the right configuration, at the right moment. Wolfgang Ketterle's group at MIT reached the condensate a few months later, working with sodium-23 rather than rubidium-87. Sodium is a lighter atom and has different technical challenges and advantages compared to rubidium, but it is also a boson and it condenses in the same basic way. Ketterle's group produced condensates with many more atoms than the initial Cornell-Wyman result. Tens of thousands, eventually hundreds of thousands of sodium atoms in a single condensate. And this larger number opened up experimental possibilities that were difficult with only a few thousand atoms. One of those possibilities was the matter-wave interference experiment, and it is one of the most visually striking demonstrations of what a Beck actually is. In a standard interference experiment with light, the kind of experiment students do in physics classes with a laser and two narrow slits, a beam of light passes through two slits and the two emerging beams overlap on a screen, producing a pattern of alternating bright and dark stripes, bright where the waves add together, dark where they cancel. The interference pattern is proof that light is a wave, that the two beams have a definite phase relationship, that they are coherent, marching in step. Kettle's group at MIT in 1997 produced two separate condensates of sodium atoms, side by side in the same trap, by splitting the original condensate in two with a laser. Then they switched off the trap and let the two condensates fall and expand freely. And as they expanded, they overlapped. And where they overlapped, stripes appeared. Alternating regions of high and low atom density, spaced with extraordinary regularity. An interference pattern, made of atoms. The same mathematics that describes light waves interfering through a double slit also describes matter waves, atoms, interfering when two coherent condensates overlap. The interference fringes were a direct visual proof that the atoms in a Beck are not individual particles in different states, moving and scattering independently, They are a single coherent wave, a macroscopic quantum state, and when two such waves meet, they interfere like any waves do, adding and cancelling in a precise, mathematically predictable pattern. This image, with the fringes in the matter, is the most direct visual argument for what a BEC is. You are seeing quantum mechanics written at a scale you can photograph. Quantum coherence, normally a microscopic and hidden thing, made large and observable and real. No solid would produce this. A cold gas would not produce this. A liquid, a plasma, none of these would produce this. Interference like this requires a single shared wave function. It requires all the atoms to be part of one coherent entity. It requires the fifth state. The condensate is not just cold matter, it is unified matter. That is the distinction. And it lives in the laboratory for seconds. While the physicists are recording it, it is already dissolving. The atoms drift apart. The trap is off. The coherence leaks away. The condensate is gone, and the atoms are individuals again. Individual rubidium atoms, or sodium atoms, drifting in the vacuum, cooling further as they expand until they hit the walls of the chamber and are absorbed. And then the cycle restarts. The atom source refills the trap, the lasers recapture and cool. The evaporation descends again, and a new condensate forms. There is something almost meditative about it if you let yourself sit with it. The repeated journey from warm to cold to unity and back again. The making and unmaking of the most ordered matter in the world, over and over in a quiet laboratory. The spike rising in the data and fading and rising again with the next run. What Cornell and Wyman had made on that June afternoon in 1995 was something no one had held before, something Einstein had predicted from the mathematics in 1924 and had not quite believed himself, something the laboratories of the mid-20th century had aimed for and found out of reach, a state of matter so fragile it lasts only seconds and so delicate that the warmth of a single air molecule would destroy it, but so perfectly ordered that it makes everything else we call matter look, by comparison, like noise. And yet, for all its fragility, it could do things that no other form of matter could do. That is where the story turns, not just inward, toward the making of the condensate, but outward, toward what it revealed, what it enabled, what it changed. The first thing Cornell and Wyman did once they had confirmed what they were seeing was look at it, really look. And the image they produced, the false color velocity distribution plot, the one that would appear in textbooks and Nobel lectures and science museums, is not a photograph in any ordinary sense. You cannot photograph a Bose-Einstein condensate the way you photograph a mountain or a face. It is too small, too cold, too brief. What you can photograph is the shadow it casts when you release it from the trap and let it fall. And a sheet of laser light passes through it, and the atoms absorb the light in proportion to how many of them are there and how fast they are moving. What appeared in that image was a sharp spike rising from a broad, low background. The broad background is the thermal atoms, the ones that didn't quite make it into the condensate, the stragglers still moving in all directions with a distribution of speeds, forming a wide, rounded mound. They are the noise. They are what normal, uncondensed matter looks like in velocity space, spread out, diffuse, democratic in their disorder. And rising from the center of that mound, narrow and tall, almost impossibly sharp, is the condensate. The condensate atoms have almost no velocity at all. They are in the lowest quantum state, moving as close to not at all as matter can move. In the image, they appear as a spike, a sudden column of color at the center, distinct and unmistakable, as though a mountain had appeared in the middle of a plain overnight. That spike was the signal. That was what 71 years of physics had been pointing toward. Cornell and Wyman saw it and knew They confirmed it with every test they could run, and then they published, and the field understood what had happened, and the world changed. Quietly, in the way that fundamental physics changes the world, not with a bang, but with a slow, deep shift in what is known to be possible. The date was the 5th of June, 1995. The number of atoms in the first condensate was about 2,000. 2,000 rubidium-87 atoms chilled to roughly 170 nanokelvin, 170 billionths of a Kelvin above absolute zero, merging into a single shared quantum state in a small chamber in a university laboratory in Boulder, Colorado. That is a small number of atoms. A single grain of sand contains something like 10 billion atoms. 2,000 is almost nothing, a rounding error in the physical world. But they were unified, they were one. And that made all the difference. A few months later, on the other side of the country, something comparable but distinct was happening. Wolfgang Ketteler is a German-born physicist who had come to MIT, the Massachusetts Institute of Technology, in Cambridge, Massachusetts, and he and his group had been working toward the same goal through 1995. They reached it in September of that year and published in November. Their condensate used sodium atoms, sodium-23, a different element, a different set of quantum properties, a different laboratory configuration. But the result was the same in the ways that mattered: a sharp spike, a unified wave, a condensate. What Ketterle's group had, though, that Cornell and Vuillemin's first condensate lacked, was scale. His condensate contained far more atoms, hundreds of thousands of them, in some of the subsequent experiments. And that larger, more robust condensate enabled something extraordinary. He made two of them. He took a single condensate and split it into two separate clouds of atoms, two separate Bose-Einstein condensates, floating in the same vacuum chamber but not touching, not overlapping, and then he released them both from their traps at the same moment and let them fall toward each other, and they interfered. You know what interference looks like if you have ever dropped two pebbles into a still pond at the same time. Each pebble makes a circular wave, and where those waves meet, they add and subtract. Where crest meets crest, the water piles up. Where crest meets trough, they cancel. The result is a pattern of alternating high and low, a grid of interference fringes spreading out across the surface of the water. What Ketterle's group saw was the same thing, but in matter. When the two condensates met and overlapped, they produced visible interference fringes, stripes of high density alternating with stripes of low density, perfectly regular, just as in the water. Matter wave interference. The thing that quantum mechanics had been saying was true since the 1920s, that particles, even atoms, even visible, macroscopic collections of atoms, behave as waves rendered visible directly in a laboratory image. This was not a theoretical demonstration. This was not an inferred result, a calculation matching a measurement. This was a picture, stripes in matter made by the wave nature of atoms recorded on a camera. If you were looking for the moment when the physics of the quantum world stopped being abstract and became something you could hold in front of your eyes, this is a strong candidate for that moment. Ketterle later described it as one of the most beautiful things he had ever seen in the laboratory. The fringes appearing in the data, that perfect regular pattern, the unmistakable signature of wave coherence. Two clouds of atoms remembering, even after separation, that they were waves. In 2001, the Nobel Committee in Stockholm made its decision. The Nobel Prize in Physics for that year went to three people: Eric Cornell, Carl Vuillemin, and Wolfgang Ketteler. The citation reads, and this is worth pausing on, "For the achievement of Bose-Einstein condensation in dilute gases of alkali atoms, and for early fundamental studies of the properties of the condensates, 71 years had passed since Einstein wrote his prediction into the literature in 1924 and 1925. 71 years of physics, of laboratory progress, of ever-improving technology for cooling and trapping and manipulating atoms. 71 years during which the condensate had been a mathematical certainty that no one could reach. And then, in a span of a few months, in 1995, two groups did. The prediction had waited 3/4 of a century. It paid off in one summer. There is something quietly moving about that timescale, if you think about it. Einstein in 1924 was in his mid-40s. He would live until 1955. He died not having seen the condensate, and yet he had predicted it. He had written it into the mathematics so clearly that when the tools finally arrived, the laser, the vacuum system, the magnetic trap, the path was already there, drawn in equations, waiting. He had dreamed it and doubted it, and the universe had confirmed it, and he never knew. The condensate, he imagined, sat in his papers for a lifetime, and then someone finally built the apparatus, and the spike appeared in the data, and a telephone rang in Stockholm, and two men in Boulder and one in Cambridge heard their names called. Physics takes its time, but it keeps its promises now. Once you have the coldest matter in the universe, the obvious question is, what do you do with it? And the answer, it turns out, is stranger and more practical than you might expect, and in some ways, more beautiful. The first thing the condensate is good for is what it has always been good for: knowing, understanding. It is the most perfect quantum system ever assembled in a laboratory. Every atom in the same state, every atom behaving coherently with every other, the whole collection described by a single wave function. That is an extraordinary laboratory for testing the deepest predictions of quantum mechanics, for pushing on the boundaries of what we understand about matter and energy and the nature of reality itself. But beyond pure knowledge, the condensate has led somewhere practical. Consider light. Light moves in vacuum at roughly 300 million meters per second. This is a constant, one of the few genuine invariants of the physical universe, written into the structure of space-time itself by the equations of relativity. In everyday materials, glass, water, air, light slows a little because it is interacting with the electrons in the material. But the slowing is modest. Light in glass moves at something like 200 million meters per second, still impossibly fast by any human standard. In 1999, a physicist named Leni Howe, working at Harvard University, did something to light that should not intuitively have been possible. She slowed it to 17 meters per second, not 300 million, not 200 million, not even 300,000 or 300. 17. About the speed of a bicycle moving briskly downhill. The speed a fit person might reach on a flat road, legs pumping, wind in their face. She did it by passing a pulse of light through a Bose-Einstein condensate. The condensate, because every atom in it is in the same quantum state, because the whole collection is coherent and unified, interacts with light in a way that no ordinary material does. The pulse enters the condensate, and the atoms of the condensate respond collectively, and the light slows. Not because it is bouncing off individual atoms in a clumsy, scattered way, but because the entire quantum medium is absorbing and re-emitting it with a precision that ordinary matter could never achieve. 17 meters per second. Light slowed to bicycle speed inside a drop of matter colder than anywhere in the known universe. And then Howe went further. She stopped it. She passed a pulse of light into the condensate, slowed it to nearly nothing, and then switched off the condensate's quantum coherence, changed the state of the atoms, and the pulse simply stopped. Stored. A pulse of light held motionless in a cloud of atoms, and then she switched the coherence back on, and the light started moving again. and emerged from the condensate and continued on its way as though nothing had happened. She had, in a meaningful sense, parked a ray of light and then retrieved it. This is not a metaphor, it is a reported, published, experimentally verified result. Light stopped and stored in a Bose-Einstein condensate and then released. The implications for quantum information, for communication, for the long future possibility of devices that work with quantum states rather than classical bits, these are still being worked out. But the demonstration alone is worth sitting with for a moment. Light is the fastest thing in the universe. It does not, under ordinary circumstances, wait for anything. It does not pause, it does not store. It moves always at its speed. And nothing we encounter in daily life changes that in any fundamental way. And yet, in a quiet laboratory at Harvard, inside a drop of matter, at a billionth of a degree above absolute zero, light stopped. The coldest matter held the fastest thing, and the fastest thing waited. There is something almost tender about that image if you let yourself feel it. The ferocious, untamable speed of light held still, for a moment, by the gentlest, most fragile, most perfectly ordered matter in the universe. Let the thought settle. There is no rush. The condensate also turns out to be useful as a clock, not in the simple sense that a condensate itself keeps time, but the physics that produces the condensate, the physics of ultra-cold atoms, of laser cooling and trapping and precise quantum state control, is exactly the same physics that underlies the most precise timekeeping devices ever built. Atomic clocks work by exploiting the fact that atoms of a given element always absorb and emit light at exactly the same frequency, a frequency set by the quantum energy levels of the atom, which are in turn set by the laws of physics and do not vary from atom to atom or from moment to moment. Cesium-133, for example, has a particular transition frequency that is used to define the SI second, the official second, the one that GPS satellites and financial networks and scientific experiments around the world depend on. The precision of these clocks, or the number of seconds they would gain or lose in a billion years, depends on how well you can isolate the atoms from disturbances that would blur the frequency measurement. Cold atoms are better atoms for this purpose. They move slowly, they spend more time interacting with the measurement field. Their resonance is sharper, cleaner, more precisely measured. The laser cooling and trapping techniques that made the BEC possible, the same optical molasses, the same evaporative cooling, the same magnetic and optical traps, are the direct ancestors of the technology inside modern atomic clocks. And modern atomic clocks are so precise that they would neither gain nor lose a second over hundreds of millions of years. Your phone knows where it is within a few meters because satellites overhead are carrying atomic clocks, and the timing signals those clocks transmit are precise enough to triangulate your position from the tiny differences in arrival time between one satellite signal and another's. The GPS system is, in a real sense, made possible by cold atom physics, by the long chain of understanding that runs from Bose's paper in 1924, through Einstein's extension, through the laser cooling work of the 1980s, through the Nobel Prize of 1997, through the condensate of 1995, to the satellite in the sky and the small glowing rectangle in your hand. The next time you navigate somewhere you have never been, following a small blue dot across a map, you are holding in your palm a very distant consequence of a rejected paper that a physicist in Dhaka sent to Einstein in 1924. Physics travels slowly, but it travels far. The cold atom toolkit also gave rise to something called the atom interferometer. Remember the interference fringes that Kettley's two condensates made when they overlapped? Those beautiful stripes of high and low density, wave crests and troughs in matter? An atom interferometer is a device that exploits exactly that effect for measurement. You take a beam of cold atoms and split it into two paths, two separate routes through space, and then recombine them, like splitting a river into two channels and joining them back together downstream. When the two streams recombine, they interfere, and the pattern of the interference depends with extraordinary sensitivity on anything that happened differently to one path than to the other. If one path passes through a region of slightly different gravity than the other, because there is a mass nearby, a mountain, a buried aquifer, a dense mineral deposit, the atoms on that path are affected differently. The interference pattern shifts. And from that shift you can infer the gravity difference between the two paths with a precision that no ordinary instrument can match. Atom interferometers are, in essence, quantum sensors of gravity. They can detect the tiny variations in Earth's gravitational field caused by what is beneath your feet, which changes as aquifers fill and drain, as tectonic plates shift, as ice sheets grow and shrink. They are being tested for navigation without satellites, an inertial guidance system so sensitive that a submarine could cross an ocean and know exactly where it was without once surfacing, without once connecting to a signal from the sky. All of this, the clock, the interferometer, the stopped light, grows from the same root. The root is cold. The root is the recognition that the quantum world is always there, in every atom, and that if you can slow the atoms down enough, cool them enough, quiet them enough, the quantum world stops being hidden and becomes the whole story. The condensate is not just a curiosity, it is a window. And through that window, built in a quiet laboratory, we have seen things about the nature of matter and light and time that we could not have seen any other way. But the story of cold, the story of how low a temperature human hands can reach, did not end in 1995. It did not end in 2001 when the Nobel was awarded. It continued, as science always continues, pushed by people who look at a boundary and ask what is on the other side of it. And in 2022, a group of scientists in Germany reached a number that made even those familiar with the field pause: 38 picokelvin. Not nanokelvin, which is already a billionth of a Kelvin, already a temperature that strains the imagination. Picokelvin, a trillionth of a Kelvin, 38 trillionths of a degree above absolute zero. Pico is the prefix that means 1 trillionth. It sits 4 orders of magnitude below nano. The gap between a nanokelvin and a picokelvin is the same size as the gap between 1 millimeter and 1 meter. It is not a small step. It is a leap into a territory that physicists had theorized about but had struggled to reach. The team was led from the universities of Bremen and Hanover in Germany, working with a drop tower apparatus, a structure that allows experiments to be conducted in free fall, in microgravity, for a brief time, not in space. On the ground, in Germany, in a tower built for this purpose, in a laboratory where the floor is beneath your feet and the sky is overhead, and everything is as terrestrial as you could want. The way they reached 38 picokelvin was, in keeping with the whole story of cold, beautifully simple in principle and fiendishly difficult in execution. They made a Bose-Einstein condensate. They cooled atoms to nanokelvin temperatures using all the tools that Cornell and Wieman and Ketterle and the laser cooling pioneers had developed and refined over decades. And then they let the condensate fall. When a condensate is held in a trap, magnetic or optical, the atoms are not perfectly still. They are squeezed into a small region by the trap, and quantum mechanics means that squeezing a particle into a small region gives it a small but non-zero momentum, a small but non-zero energy. This is Heisenberg's uncertainty principle at work. You cannot specify both position and momentum perfectly, so confining the position costs you in the momentum budget. The atoms have a tiny residual jitter, a quantum restlessness that cannot be removed by any amount of conventional cooling as long as they are trapped. But if you turn off the trap and let the atoms fall freely, if you remove the walls, the condensate expands. Slowly because it is cold, very slowly because there is almost no energy to drive the expansion, and as it expands, the residual momentum is gradually shared across a larger and larger volume, spread thinner and thinner until the effective temperature, the temperature as measured by the spread of velocities, falls below anything achievable in a trap. To reach 38 picokelvin, the German team used the drop tower to create a few seconds of microgravity, a brief window where the atoms were not pulled toward the floor, where the condensate could expand in all directions without one direction being spoiled by gravity, and let the condensate expand as slowly as it could. The result was 38 trillionths of a Kelvin, the coldest temperature ever recorded for a physical sample, the coldest matter ever achieved, the stillest, most ordered, most deeply quantum state of matter that human hands have created. And it was done in a tower in Germany in a laboratory on a Tuesday or a Wednesday or a Thursday by people in ordinary clothes, drinking coffee, checking their instruments. The coldest spot in the universe, made at the bottom of a drop tower on the surface of a planet orbiting an ordinary star. Now, the universe is old and vast, and it contains many cold things. The space between the galaxies is cold, a few Kelvin above absolute zero, warmed only by the cosmic microwave background, the faint afterglow of the Big Bang, which fills all of space at a temperature of about 2.7 Kelvin. There are molecular clouds in the interstellar medium that are a few Kelvin or a few tens of Kelvin. There is a nebula, the Boomerang Nebula, a dying star surrounded by an expanding shell of gas, where the rapid expansion of that gas has cooled it to about 1 Kelvin. The Boomerang Nebula is the coldest known natural object in the universe, roughly 1 Kelvin colder than the cosmic background, colder than interstellar space. 1 Kelvin. And the laboratory in Germany reached 38 trillionths of a Kelvin, a number 26 billion times smaller. The coldest thing in the universe by a staggering margin is not out there in the dark between the stars. It is here, on this planet, in a building made by people. That is worth sitting with for a moment, in the quiet of wherever you are. The universe does not on its own get very cold. It does not have the patience or the ingenuity. Stars burn, gas falls together and heats. The cosmic background is warmer than any BC. Only in a laboratory with lasers and traps and vacuum chambers and evaporative cooling and, now, free-fall expansion in a drop tower. Only there does matter get quiet enough to become one thing. The universe makes hot things easily. It takes human hands to make the coldest, and perhaps that is one of the stranger, quieter aspects of what we are. That we are made of this universe, made of the same atoms as the stars and the nebulae and the cosmic background radiation, and yet we can do something the universe itself cannot do. We can build a place where matter comes to rest. Not absolute zero. The third law will not allow it, and even the picokelvin record is not absolute zero, only close, always approaching, never arriving, but close enough to see what happens. Close enough to see the condensate form. Close enough to see the matter wave interference fringes and the light slowing to bicycle speed, and the spike rising in the false color plot. Close enough to see what matter is when it is allowed to be still. And what matter is when it is allowed to be still is not many things, it is one thing. Thousands of rubidium atoms, or sodium atoms, or the atoms of whatever element the experimenters choose, each of them a separate particle with its own position and momentum and quantum state, each of them an individual, chilled until the individuality dissolves. Until the de Broglie wavelengths swell and overlap and merge, until the thermal noise that keeps them distinct is reduced to almost nothing, until they surrender their separateness, not because they are forced to, but because at the lowest energies, the lowest temperatures, the lowest quantum states, separateness is simply not the most stable configuration. One state is lower in energy than many states. One wave is more stable than many waves, and so, given the cold and the time and the right kind of atom, the many become one, the superatom, the condensate, the fifth state of matter. There is a word for what happens to the condensate, and it is a word that appears elsewhere in physics, in contexts that feel, on the surface, quite different. The word is coherence. Coherence is what a laser has that an ordinary light bulb does not. A light bulb emits photons in random directions, random phases, random frequencies, all going their separate ways, not coordinated with one another. A laser emits photons all in the same direction, the same phase, the same frequency, all marching together, all part of one wave. The coherence of the laser is what makes it able to read a disc, or cut metal, or measure distance with extraordinary precision. Incoherence is noise. Coherence is power. The condensate is the same thing, but for matter. Ordinary matter, the atoms in the air around you, the molecules in the cup of tea on your bedside table, the atoms in the walls and the floor and your own skin, is incoherent. Each atom going its own way, vibrating at its own rhythm in its own state. All of them statistically described, not individually known. The randomness is so deep, so fundamental that we have no choice but to work with averages, with distributions, with temperatures and pressures rather than individual quantum states. The condensate is coherent matter, all atoms in the same state, all atoms part of one wave. And coherence, as the laser shows us, is what makes the impossible possible. Stopped light, interference fringes from matter, quantum simulation of materials too complex to calculate, gravity sensors of extraordinary precision, timekeeping of unearthly accuracy. All of it flows from coherence. All of it flows from the ability to quiet matter until it stops being many and becomes one. You have been drifting with this story for some time now through the history and the physics and the laboratories, through the equations and the experiments and the names and the years, and you may be wondering, as a listener, lying still in the dark sometimes does wonder, what any of this has to do with you. Here is what I think it has to do with you. Your body right now, and the body lying in the bed, resting against the pillow, breathing slowly in and out, is made of atoms. Of course it is, everything is, but the atoms you are made of are not different from the atoms that Cornell and Wyman coaxed into their first condensate. They are not different from the sodium atoms in Kettley's laboratory that produce those matter wave interference fringes. They are the same atoms, the same quantum particles, obeying the same quantum rules, carrying in their structure the same de Broglie wavelengths, the same wave nature, the same capacity for coherence. At the temperatures of your body, warm, alive, humming with the biochemical activity of being a living thing, the quantum wave nature of your atoms is hidden, washed out by the thermal noise. Each atom too warm, too fast, too energetic to overlap with its neighbors. The coherence is lost in the noise of life, but the coherence is not gone. It is still there in the mathematics, still there in the quantum mechanics of every atom. The wave nature that produces the condensate is the same wave nature that gives the atoms their energy levels, their spectral lines, the precise frequencies that atomic clocks use to define the second that GPS depends on to tell you where you are. All of that is the same physics, All of that is running right now in every atom of your body. You are not separate from the quantum world. You are made of it. And there is something else. The condensate is a story about stillness. Every step of its creation, the laser cooling, the optical molasses, the evaporative cooling, the magnetic trap, is a step toward stillness, a step toward quieter, a step toward slower. The atoms are always being brought to rest gently, carefully, by systems that understand that the goal is not to force or constrain, but to encourage, to give the atoms less and less energy until they arrive, of their own quantum nature, at the lowest state. And in the lowest state, they stop being separate. This is the part I want to leave you with as you lie still in the dark, as the night settles around you, as your breathing slows. There is something in the physics of the Bose-Einstein condensate that resonates with the experience of sleep itself, of rest, of the quieting that you are in the middle of right now as you listen to these words. You spend your days as many things, many thoughts, many concerns, many separate tasks and identities and roles. The person at work, the person at home, the person managing 1,000 small decisions, the person with 100 things left undone. The thermal noise of a life fully lived, and then you lie down, and the noise decreases, and the separate things begin gently to let go of their separateness. Sleep is the body's own version of cooling, not to a billionth of a degree. The body needs its warmth to live, but a cooling of urgency, of alertness, of the frantic individuality of a fully conscious, fully engaged mind. The thoughts slow, the muscles soften. The boundary between self and world, so sharp in the daytime, becomes a little blurred. You do not become a Bose-Einstein condensate, but something in the direction is the same. The many things that you are, quieted until they settle into something simpler, something more still. The physicists who built the first condensate were chasing a specific quantum state. They were not chasing rest or peace or any of the things that sleep is for. They were following mathematics and laboratory protocols and the very specific goal of cooling rubidium atoms to 170 nanokelvin. But the shape of what they found, the merging of the many into one, the beauty of a thing surrendering its complexity for a deeper, quieter order, that shape is older than physics. It is something that living things have been drifting toward every night since there were living things. The condensate is a window into the deepest quiet that matter can reach. You, right now, are heading somewhere in the same direction. Let yourself go. The atoms are patient, the physics is patient. The mathematics that Einstein wrote in 1924 waited 71 years, and it was still there exactly where he left it, when Cornell and Wyman finally opened the door. Your thoughts will still be there in the morning. Whatever is left unfinished will still be there. The world will still be there, in all its noise and urgency and beautiful disorder. But right now, at this moment, this breath, something can be still. We have traveled a long way tonight, you and I. From a desk in Berlin in 1924, where a physicist in his mid-40s read a stranger's rejected paper and saw, in its equations, something extraordinary waiting. Through the early quantum mechanics, the wave equations, the boson and fermion families, the Pauli exclusion principle, the strange democracy of identical particles, through the superfluid helium climbing its container walls in 1937, history's first hint that Bose-Einstein behavior was real. Through the slow mechanism of cold, the lasers set to exactly the right frequency, the atoms wading as if through thick syrup, the evaporative cooling no different in principle from the steam rising from a cup of tea on a cool morning. Through the magnetic traps and the ultra-high vacuum chambers, the extraordinary fragility of the condensate destroyed by a single room temperature molecule, alive for seconds. Through the spike in the false color image on the 5th of June, 1995 in Boulder, Colorado. Through the matter wave interference fringes in Cambridge, Massachusetts, two separate condensates released to overlap and produce, in matter, the striped pattern that water makes when two pebbles fall. Through the light, slowed to bicycle speed, 17 meters per second, in a Harvard laboratory in 1999, and then stopped, and then retrieved. Through the atomic clocks precise enough to neither gain nor lose a second in hundreds of millions of years, and the GPS satellite overhead, carrying that precision across the sky to the small glowing rectangle in your pocket. Through the atom interferometers, sensing the faint pull of gravity with such delicacy that they might one day navigate the deep ocean without a single signal from the sky. Through the optical lattices, the quantum simulators, the condensate used as a laboratory for materials too complex to calculate, a stand-in for the world of electrons in solids. Through the Nobel Prize, awarded in Stockholm in 2001, 71 years after the prediction. And finally, to a tower in Germany in 2022, atoms in free fall, expanding, cooling as they expand, spreading their last remaining quantum restlessness across a volume of space larger than any trap could contain, reaching 38 picokelvin, 38 trillionths of a Kelvin above absolute zero, the coldest temperature ever recorded, the coldest matter in the universe made by human hands on a Tuesday in a building on this planet. That is where we have been. And here is where we are. You are made of the same atoms. You carry in your body the same wave nature, the same quantum rules, the same fundamental physics that makes the condensate possible and makes the atomic clock tick and makes the GPS know where you are. The universe that produced the Boomerang Nebula and the cosmic microwave background and the dark spaces between galaxies also produced you. The same particles, the same forces, the same quantum mechanics running in every atom. You are not outside the story. You are the story, wearing a different shape. And the story tonight is one of cooling, of quieting, of the many things gradually letting go of their insistence on being separate, drifting towards something that is not nothing, but is simpler than the busy individual thermal noise of a warmer state. The condensate does it with lasers and traps and vacuum chambers and extraordinary precision. You do it by lying still in the dark and letting the night do its slow work. Where are you listening from tonight? What time is it in your corner of the world? I find myself wondering, as I always do at the end of these journeys, whether you are in a city with rain on the window, or somewhere quiet with the sound of wind, or somewhere warm or cool, or somewhere in between. Whether the lamp is still on or the room is dark, whether you made it this far or drifted off somewhere back in 1995 when the spike appeared in the data. Either way is right. Either way is exactly what this was for. If something here, or one idea, one image, one moment of quiet wonder, is what you carry into sleep tonight, that is enough. The fifth state of matter waiting at the edge of absolute zero, thousands of atoms merging into one. Einstein's prediction, patient for 71 years, light, stopped by the coldest matter in the universe and then released. You can carry that gently, it weighs almost nothing. If you enjoyed this slow journey tonight and would like more nights like this, a gentle like and subscribe means a great deal. Small creators like me rely on your support to keep these going. And if you have a moment, leave a comment telling me where you are and what time it is there. I read them, and I am always glad to know. Sleep well, fellow voyager. The next journey keeps until you wake.